All right, today we're doing the Conduction Lab. So the Conduction Lab. All right, so there's three methods of heat transfer that we've looked at. Radiation is the energy it travels through electromagnetic waves, like sunlight. It can travel through empty space. When we talked about convection, that's when, like, if you have water and there's one section where it's warmer and one section where it's cooler, the warmer, less dense section will rise, the cooler, more dense section will sink, and you get this circular motion going on. So that's convection. But what we're looking at today is conduction, and that's the method of heat transfer that takes place in solids. So we're going to observe how that takes place. So what we're going to do for the experiment is we're going to have two cups. One cup, we're going to put hot water in. So there's some teapot right there, some boiling water in. And the other cup, we're going to put some ice water in. So I have a beaker here with a bunch of ice water. So we're going to put those two cups like that. And we want to get the heat to move from the hot cup to the cold cup. So what we're going to do is we're going to connect those two cups with the metal bar like that. Right? Now, as it stands right now, what would happen is a lot of the heat would get lost off the top of that hot cup. So to limit how much that energy is going to get lost, what we'll do is we're going to put like little styrofoam lids on here. It'll help prevent the water from being prevent the energy from the water from being lost. All right, so we're going to put little lids on. All right. So I'm going to put the hot water and cold cup water, put the bar in, and then we're going to take temperature readings for 20 minutes. All right. So I'll do the cold water in here first. Boiling water. Take your initial temperatures. So it's boiling and right at ice water, so it's 100 Connect them, and start the timing. All right, so time 0, again, the hot water is boiling, so it's right at 100 degrees Celsius. And the cold water is right at 0. Okay, it's just been just about 1 minute, and I'm at about 90 and still at 0. Okay, coming up on 2 minutes. At 1:84. All right, it's about coming up on 3 minutes here. Got 83 and 2. All right, coming up on 4 minutes here. We got 82 and 2. Coming up on 5 minutes. All right, it's 80 and 2. Coming up on 6 minutes here. $79 and 3. Okay, coming up on 7 minutes. 78 and 3. 78 and 3. Okay, coming up on 8 minutes. $76 and 3. Okay, 9 minutes. $75 and 4. 75 and 4. Okay, 10 minutes. Coming up on 10 minutes here. $74 and 4. All right, so coming up on 11 minutes. $73 and 4. All right, so coming up on 12 minutes. 71 and 4. Okay, 13 minutes. It's 70 and 5. 70 and 5. All right, 14 minutes is just about coming up here. All right, 14 minutes. Yeah. 69 and 6. All right, 15 minutes. Is 68 and 6. All right, just about 16 minutes now. Is 67 and 7. All right, coming up on 17 minutes. We got 66 and 7. All right, up to 18 minutes now. It is 65 and 8. All right, 19 minutes. $63 and 8. Almost there. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. All right, last reading. Got 62 and 9. All right. So what you should notice here is if you look at how much the temperature's changed, if I look here from cold cup, I went from 0 to 9 degrees. So the cold cup went up 9 degrees. The hot cup went from 100 to 62. So the hot cup dropped 38 degrees. All right? So there's a big difference between how much the hot cup lost and how much the cold cup gained. Right. Now, so you have to think, where could we be losing energy? Well, this wasn't a perfect seal here, so you would have lost a little bit of heat kind of coming off that there. But that's not the main place where it was losing heat. The main place it was losing heat, if you think about it, is this metal bar right here, right? I could touch that metal bar right now. That metal bar is hot. Not only is the metal bar hot, but I can feel, if I put my hand above the metal bar, I can feel heat coming off of the metal bar. So what's happening is, so where a lot of this heat went, well, some of it's actually still in the metal bar itself. But a lot of the heat is this bar is radiating heat to the air before it even gets to the cold cup. So that's where we're losing a lot of the heat right there, is this energy being radiated to the air. Okay. Now, if I wanted to change this experiment to make it so that more of this energy got to the cold cup, there's a few things I could do. One thing I could do is I could insulate that metal bar. All right, so here's a bunch of foam on the bar. So if I use the insulated bar, that would limit how much energy was escaping through radiation, and that would make it so more of the heat got to the cold cup. So that temperature would have been up more, all right? Another thing I could have done is I could have used a different metal bar. So if I used a shorter metal bar, maybe it was half as long, then there would have been less distance for the energy to travel, and then you wouldn't lose as much that way. Or I could have combined it. I could have done a shorter bar that was insulated, and it would have been even better yet. So there's a bunch of places where this system is losing energy to the environment. All right, now, what you're going to have to do with this data is you're going to make a graph of this data. And on your graph, all right, on your x-axis, on the independent variable, are the numbers which you knew what they were going to be ahead of time. I knew I was going to take a temperature reading every minute. So down here on the graph, you're going to have time in minutes. And we're going from 0 to 20, so you got to make sure that you pick a scale that works from 0 to 20. All right. Now, what we're going to be graphing is temperatures, and our graph's going to have two lines on it. You're going to have one graph for the hot cup and one graph for the cold cup. So we got to make sure we can fit both the hot cup data and the cold cup data on there. So if I look, of all the data I have, the lowest temperature I have is 0. So on the side here, I'm going to have 0. And then my highest temperature I have, I scanned through all my data. The highest temperature I have is 100. So I got to make sure that my graph, I can fit in everything from 0 to 100 on there. So you have to pick a scale with even increments that goes from 0 to 100. And this would be temperature in degrees Celsius. So if you have colored pencils, it would be better if you did this in colored pencils. If you don't, it's not a huge deal. You just want to make sure you label it. So you're going to plot all your hot cup data. So it's going to be a line graph. So you're going to be plotting your points and then connecting it with a line. Then you're going to have to plot all your cold cup data, and you plot that. And then connect that with the line. So your graph should roughly look about like that when you get done with it. Now, places on the graph, you could tell how fast of a temperature change there was by how steep the graph is. All right? Now, if the graph is a constant steepness the entire time, that means your temperature change was constant. Places where the graph is steeper, that means there was a big temperature change, or a big rate. There's a big rate where the line is steeper. Where the line's flatter, that means there's a smaller rate. All right, so you can look at the graph and figure out where the graph is speeding up or where it was slowing down by how steep the line is on there. But your graph should look roughly like that when you get done. All right, so you got to plot your data, make the graph, and then you got to answer the questions for the lab. And that is it.